In the quiet expanse between Mars and Jupiter, something strange has been unfolding. A visitor, catalogued as 3IATLAS, our third confirmed interstellar object, has begun to change its form. The latest ESA ExoMars and ground-based observatories have captured a transformation that defies the textbook image of a comet. Instead of the graceful tail that sweeps away from the sun, we now see a curious counterstructure. A forward-pointing anti-tail, shining faintly in the sunward direction. The geometry is rare, but not unheard of. The question is, what exactly are we looking at? To the untrained eye, an anti-tail can appear as a violation of cometary logic. Yet in classic celestial mechanics, perspective can play tricks. When a comet's orbital plane aligns closely with that of Earth, the ecliptic, dust sheets can seem to project toward the sun, even when they are physically trailing behind. A phenomenon of optics and alignment, not propulsion. But with 3IATLAS, geometry alone may not be enough. Its faint brightness, erratic photometric curve, and minimal outgassing suggest an object both larger and denser than expected. Perhaps a few miles across, with a surface more akin to carbonized metal than porous ice. And that leads us to the central debate. Is this forward glow just sunlight scattering off dust, or the trace of non-gravitational acceleration, a controlled, or at least directed, form of thrust? In aerospace dynamics, non-gravitational acceleration is the polite term for any motion that can't be explained by gravity alone. For comets, that typically means asymmetric outgassing, jets of vaporized ice pushing the nucleus slightly off its predicted course. But for 3IATLAS, those jets appear too weak, too uniform, and far too persistent to account for the orbital discrepancies observed. Tracking from ExoMars, Gaia, and Earth-based radar arrays reveals deviations of just a few millimeters per second. Subtle, yet significant, when projected over millions of kilometers. Something is nudging it, something consistent, something deliberate. This is where orbital mechanics meets imagination, and the boundary between the natural and the engineered begins to blur. Let's start with what we know. 3IATLAS is now behind the sun, hidden in the glare, invisible to optical telescopes. Its perihelion, the closest approach to the sun, will occur on October 29th, a moment of both maximum heating and maximum orbital leverage. If this object is natural, it will behave as physics predicts. Solar radiation will bake its surface, volatiles will vent, and its orbit will bend in ways calculable by the standard cometary model. But if it is not, if the so-called forward-pointing tail is evidence of directed energy or controlled orientation, then the days surrounding perihelion could reveal something never before witnessed. A maneuvering interstellar body. A natural anti-tail fades as geometry changes. A driven one maintains vector stability. That is the test, and that is why October 29 is so pivotal. Behind the sun, the object is momentarily cut off from our instruments. A blackout window in both radio and optical domains. When it re-emerges in November, analysts across ESA, NASA, and independent observatories will compare predicted trajectories against measured ones. Any residual deviation, any drift unexplained by solar radiation or outgassing, will become headline material. The physics of this encounter reads like a lesson in orbital optimization. Before its solar passage, 3IATLAS skimmed near Mars, performing what some analysts describe as a pseudo-gravity assist. Not a close encounter, but a passage within a range where Mars' weak gravitational influence could have subtly altered its energy state relative to the Sun. The pattern evokes what engineers call an Oberth effect trajectory, using the gravitational well of a planet to gain kinetic advantage from thrust applied near perihelion. It's the same principle humanity uses for interplanetary slingshots. But in this case, no thrusters are known to exist. If this were a natural rock, its orbital energy should remain passive. If not, if a minute thrust was applied during the Mars arc, then perihelion could serve as an Oberth test, using solar proximity to boost velocity or even achieve partial solar capture. The idea sounds speculative, but it's testable. We can model it. We can measure it, and soon we will. As it dives into solar conjunction, the instrumentation load shifts. ESA's ExoMars Trace Gas Orbiter continues its plasma and dust observations from the Martian frame. SOHO and Stereo spacecraft will track solar corona transients that could hint at reflective debris or ejecta. And the Parker Solar Probe, deep within the inner heliosphere, might capture the faint whisper of dust wave signatures, ripples in solar particles where 3IATLAS once passed. In the precision language of mission telemetry, this is the data window that defines theories. Are we witnessing sublimation from a frozen core, fragmentation from structural stress, or the controlled vectoring of a hollow shell adjusting its trajectory through microthrust? The next critical date comes in December 19th, when the object crosses its closest approach to Earth's orbital domain. At roughly 0.6 astronomical units, it won't be a visible spectacle, but for radar and optical interferometers, it's prime time for measurement. Should the trajectory show an unexpected change between October and December, a non-ballistic curve inconsistent with radiation pressure, the implications would ripple through every field from astrophysics to astrobiology, and the story doesn't end there. Later, as it drifts toward the orbit of Jupiter, the Juno spacecraft, equipped with sensitive radio instrumentation, will listen, not for voices, but for anomalous spectral signatures carrier, like tones, polarization shifts, or structured noise that could indicate artificial emissions. So far, the cosmos has been silent. But silence itself is a kind of message. To appreciate why all this matters, we must revisit the precedent. Our first interstellar object, Oumuamua, arrived in 2017 with its own riddles, a cigar-like shape, tumbling motion, and a mysterious acceleration that seemed too smooth for outgassing and too faint for reflection. It sparked headlines about alien probes, solar sails, and light-driven relics. But the data was sparse, the viewing window brief, and the debate unresolved. Then came 2I Borisov, the second interstellar visitor, a model citizen of comet physics, complete with a classic tail and well-behaved outgassing. For a moment, order returned. And now 3IATLAS has reopened the question, not by flamboyant activity, but by its restraint. By what it doesn't do, by what we don't see. No explosive jets, no wild tumbling. Just a measured glide, a mild brightening, and a forward-pointing feature that refuses to conform. For mission scientists, this is the golden zone between speculation and discovery. Every anomaly must pass through the crucible of physics before it earns its mystery. That is why the analysis now hinges on falsifiable predictions. If 3IATLAS is natural, then its brightness will decline post-perihelion according to a predictable photometric decay. Its trajectory will match the sum of gravitational and radiation pressure effects within error margins of 1/10 md dies SDAO. Its tail will fade as Earth's viewing geometry shifts beyond the ecliptic alignment. If it is not, if a controlled or semi-controlled system is at play, we might observe a trajectory deviation inconsistent with solar radiation pressure models, a sustained forward emission independent of geometry, a measurable change in spin state or albedo unrelated to solar heating. Each outcome is measurable, verifiable, and open to global scrutiny. That's the essence of the scientific method: no belief, no hype, just data. Meanwhile, visualizations pour in from citizen astronomers, agencies, and simulation labs. Computer models reconstruct how an anti-tail forms when the observer's line of sight intersects the dust plane. Others test low-thrust simulations, continuous acceleration vectors of 10th mm/CRSDO, and find that even such faint forces could reproduce the observed drift. The question remains, what engine could sustain that across interstellar space? The answer, for now, is none that we know of. But nature is full of mechanisms that mimic intent. Charged dust interacting with solar wind can self-organize into coherent streams. Porous carbon composites can emit anisotropic radiation that mimics control. And magnetic induction across conducting layers could create self-correcting torques. In short, physics can perform magic without intelligence. The burden of proof remains on us. Back on Earth, high-resolution spectrographs from Chile and the Canary Islands attempt to read the fingerprint of 3IATLAS's composition. Preliminary results hint at a nickel, dominated signature with trace carbon and silicon, a blend more metallic than cometary. If verified, this composition alone could explain the muted activity, a refractory body with little volatile material to sublimate. That would make 3IATLAS less a comet, more a planetary shard, a remnant from a disintegrated system, polished by radiation over alms. Yet, even that hypothesis leaves the trajectory puzzle intact. Why the gentle acceleration? Why the coherent ante-tail alignment through multiple viewing angles? Every answer births another question, and that is the hallmark of true discovery. As October 29 approaches, observatories brace for blackout. No instrument can stare through the solar glare without risking damage. For roughly 3 weeks, 3IATLAS will vanish behind the corona. Unseen, unmeasured, unknowable. In that absence, speculation will surge. Some will claim disappearance. Others will anticipate a flare, a split, or even controlled redirection. But the cosmos does not perform for headlines. It simply moves according to law. When it re-emerges in mid-November, we will compare prediction to observation, line by line, vector by vector. The orbit will either align or it will not. And in that single difference lies the story of whether this visitor obeys the same rules as everything else that drifts between the stars. For engineers, the fascination runs deeper than mystery. It's about what's possible. If this object truly demonstrates microthrust consistent with radiation-driven control, it could validate technologies humanity only dreams of: light, sail stabilization, passive orientation control, and resource-efficient interstellar drift. In other words, the mechanics of traveling the void without fuel. If 3IATLAS is natural, we learn from its efficiency. If it's engineered, we learn from its existence. Either way, the knowledge expands. As the months unfold, the world will watch 3 milestones. October 29, perihelion, the make or break solar geometry test. December 19, Earth close pass for radar and optical confirmation. And spring 2026, the when 3IATLAS drifts toward Jupiter's domain, where the Juno probe will quietly listen. Every frame, every photon, every spectral whisper will contribute to a collective understanding that reaches beyond curiosity, toward the fundamental question of whether interstellar space is empty or quietly occupied by relics of intelligence that predate us. For now, the narrative remains grounded. No proclamations, no certainty, just a data-driven pursuit of the unknown. The story of 3IATLAS is not one of aliens or miracles, but of a civilization learning to recognize the subtle fingerprints of physics written across the solar system. And as our instruments sharpen, as our algorithms evolve, the cosmos grows a little less silent and a little more human. Because every anomaly, every unexplained acceleration, every faint whisper of data is not just an astrophysical event. It's an invitation. An invitation to look closer, to measure deeper, to ask again what we think we know about matter, motion, and intent. And so, as the object slips behind the sun, our senses wait. The silence before perihelion is not absence, it is potential. And when that potential returns to view, whether as dust, debris, or design, we will be ready to record it, to learn from it, to understand it. In a universe defined by gravity and light, perhaps the greatest discovery is not what 3IATLAS is, but that we dared to notice at all. As the light of the sun swallows the object, instruments fall silent. For a few weeks, 3IATLAS is hidden, a shadow among plasma streams, a silence inside the solar wind. We wait, and in that waiting, we glimpse the essence of science itself, the discipline of patience, to observe, not to believe, to test, not to assume. Soon, the object will re-emerge, faint, altered, and speaking once more in the language of reflected light and orbital vectors. Every pixel captured, every photon timed, every spectral shift compared against prediction will either confirm our equations or rewrite them. And that is the beauty of this pursuit, that the unknown is not a void, but a mirror. It reflects our own drive to understand, to reach, to measure the silence between stars. Whether 3IATLAS is ice, alloy, or something neither. Whether it drifts by chance or by design, it reminds us that discovery begins not with certainty, but with curiosity. Every question is a signal, every anomaly a frequency waiting to be tuned. Because in the end, it isn't the object that matters most. It's what it awakens in us. The urge to look upward, to listen deeper, and to never stop decoding the quiet messages of the universe.